Welcome to lesson 3 of 7 in assessing the accuracy of remotely sensed data. So this is part 3 where we're talking about the methods and analysis for positional accuracy. I'm Russ Congalton, and I'm glad that you've joined me to dig into this together. So the objectives of the lesson are as follows. There's 5 of them. 1, to understand reference data collection, including the sample design, placement, and distribution. Make sure that we define and demonstrate what root mean square error is. Discuss the issues that come along with the National Standard for Spatial Data Analysis and SSDA. You'll see how important that is. And then we'll give some examples showing both horizontal and vertical positional accuracy assessment. You'll see that that gets fairly complex, and you might have to dig in and watch this a couple of times to understand it. There are a lot of equations there that are not difficult, but if you're not an equation person, it takes a little bit of time to get it. Okay, and then lastly, show how the new ASPRS 2014 standard really brings us into the digital age and solves some of the problems that we've had in the past. So here we go. Reference data sampling and design. Okay, so anytime we do any kind of accuracy assessment, whether it's thematic or positional accuracy assessment, it's really the collection of that reference data that's important, right? We're going to compare the reference data to the map. We've got some samples, and we need to make sure that we collect those samples, that reference data, in a valid way. Okay, so a couple of criteria. 1, we need data independence. The reference samples that we collect have to be different. They can't be the same. They have to be different than anything that was used as control points. In other words, if we collected some data to make the register the map to the ground, okay, we can't use those same control points to now test how good a job we did. We need a completely independent data set. That's well understood in statistics, but you'd be surprised for positional accuracy assessment how often that's not the case. And so please pay attention to that. Okay. Also, that source of reference data, which, as you remember, we're not calling ground truth anymore. We're just calling it reference data. It must be from an independent source of higher accuracy than the map. Okay, so if the reference data is worse than the map, then it's not going to be able to tell us anything. We need that to be of higher accuracy. We want it to be the best it can possibly be. The number of samples that we need. The standard that we use, NSSDA, the National Standard for Spatial Data Accuracy, requires a minimum of 20. Okay, so more recent standards, and we've talked about that in the last module, require a minimum of 20 points per ground cover class, per map class. Okay, and really, if you think about it from a statistically rigorous situation, remembering the central limit theorem, it'd be great to have 30 samples per map. Okay. You'll see that there are a number of studies that have been done where they have 4 or 10, sample points that they use, and they come up with an analysis based on that. And that's simply not sufficient. So please make sure you understand what's going on here with the sample design. Okay. As far as sample placement and distribution goes, again, the goal is to have well-defined points that you can accurately locate, that represent a feature for which the position is known to a high degree of accuracy. Okay, so we want to pick points that we can easily identify. That gets more challenging if we go into forested environments and things like that. Therefore, we've talked about that already. Okay. Distributing the points is very important as well. You can see that they have to be distributed across the entire project. You can't just pick the places where it's easy to put the points, where the points are easily identifiable. You have to make sure that they're spread out throughout the map. And so ASPRS back in 1989 suggested this approach. And that is that you divide your map into quarters, and then you make sure that at least 20% of the samples occur in each of those 4 quadrants. Okay? If you do that, then you're going to get a good distribution of points across your map. And then you also want to minimize spatial autocorrelation. Remember, spatial autocorrelation has to do with the relationship between the samples, whether they're If there's an error there, you'd have a positive autocorrelation, then you don't want those things to be collected very close to each other. You want to spread them apart. And so you can see that what's being done here is you take the diagonal of your study area. Okay, now obviously it doesn't always have to be exactly a square, but you could, make it into a square or whatever, a rectangle. And then you make sure your points are D, the diameter, divided by 10 distance apart. Okay, so you see that on the graph or on the little illustration on the side here. And hopefully that helps you to understand how you would make sure you spread the data apart. Okay, so the samples are spread apart by making sure that there's at least 20% in each quadrant. There has to be 100%, so 25, 25, 25, 25 would be fine, but if you don't quite get that, at least 20% in each quadrant, and then make sure that the samples are at least the diameter divided by 10 separate from each other. So that takes care of sample placement and distribution. If we get to the analysis, we need to start understanding root mean square error, okay, RMSE. We mentioned this a number of times already. Positional accuracy assessment relies on these estimates of root mean square error. And remember that if we're doing just vertical accuracy assessment, just one dimension, the dimension Z or the elevation, you calculate root mean square error one way. If you have horizontal error, you're talking about two dimensions, X and Y, then we're talking about a slightly different calculation. And root mean square error is usually stated at some level of confidence. So if you had a basic statistics class, you understand, at the 95% confidence level or at the 99% confidence level. That's what we're talking about here. Okay? So how do we calculate root mean square error? Well, it's very, very simple. It's not as complicated as maybe you think it looks. It's the square of the errors, okay? And then you take the square root of it. Why do we square the errors? We square the errors because in some cases, the error is going to be positive. In other cases, the error is going to be negative. And if we didn't square them and we tried to add up all the errors, you can see that they could potentially cross out because some are positive and some are negative. Another possibility would be to take the absolute value of those. And some people have suggested doing that. But traditionally, we calculate root mean square error. Okay, and so it's the square of all the errors, and then you take the square root of it. Okay, and that's what the root means. Okay, so you can see here's the equation. It's pretty straightforward. You can see that EI is defined as the reference minus what the image says or what the map says. Okay, and you do that for each sample in your map. So the 20 samples or 30 samples that you collected, and you're fine. Okay, so root mean square error, it's the square root of the sum of all the errors squared. Okay, and it's the average of that, so divided by n. So we get into a little bit of statistics and a little bit of probability. And so you remember from the graph on the right here, the standard normal distribution. Okay, that's the Z values, and we all know about that. And so you have the mean there. And if you assume a normal distribution, then we know things about the probability. And so you can see that NSSDA is represented in the 95% confidence. You can also have other standards. There's something called the map accuracy standard that uses 90%. There's other standards you can see there that use 50%. Don't get confused by that. And so root mean square error minus the Z value, okay, at the 95% confidence level, if you want to do that. And then you put the mean value in there, and then root mean square error plus the Z value times S. Okay, so it really comes down to the root mean square error plus or minus Z, which is the statistic, times the value S, which is the variance, okay, standard deviation. So you have to remember that the interval is not a measure of confidence. It's merely an estimate of the distribution of errors at some specified level of probability, assuming that the errors are normally distributed. So there's a whole bunch of assumptions in here. And so you can calculate a confidence interval on root mean square error using the equation below. Okay, we're going to apply this to a real example so you can kind of see what's going on. Okay, so here's an example. If I had an estimated root mean square error of 20 centimeters with an estimated error standard deviation of 4 centimeters, and then I want to estimate the interval for within which 95% of the errors will occur, and we assume that the errors are normally distributed, then it's a really straight process, okay? So all you're doing is calculating root mean square error. It's the sum of the errors squared, right? And then you're looking up that z value in the standard normal table, or you go online and find it, and it equals 1.96. Everybody tends to remember that if they've had a few statistics classes. And then we can just plug into the equation from the previous slide. Remember, root mean square error plus or minus the z value, in this case 1.96, times the standard deviation. Okay, so we've got root mean square error of 20 minus 1.96 times 4, and then 20 plus 1.96 times 4. And so then we know that 95% of the errors will fall within that range, which happens to be 12.16 centimeters to 27.84 centimeters. So we're getting a measure of the range or the distribution of our errors in our map. That's what RMSE does for us. Okay. Remember that we've got NSSDA, so the National Standard for Spatial Data Analysis or Assessment or Accuracy, whatever term you like to use there, okay? And there's some issues with that. That is the standard that people use. And once you've calculated root mean square error, you can calculate NSSDA from that. However, there's a problem in that the incorrect equation is used in NSSDA. Okay, NSSDA assumes that the root mean square error is 0, and therefore it incorrectly inserts root mean square error for the standard deviation in the interval equation, and that's not the way it should be done. Okay, there's a problem with that. Okay, so if you're doing vertical accuracy, just Z, then NSSDA assumes that the error interval can be estimated using the equation whatever zi, that 1.96 at the 95% confidence interval times the root mean square error. And in our case, that would be 1.96 times 20, or 39.2 centimeters. So that's now saying the NSSDA calculation is 39.2 centimeters. However, the issue is here that, one, it's assuming that the mean error, root mean square error, is 0, and that's not true. Okay, so you got a problem going on there. So the only time that the NSDA statistic will correctly estimate the error interval is when the mean error equals 0, and then the estimated mean error and the estimated standard deviation of the errors are equal to one another. And so that's not the case in most situations. The good thing about this is that a lot of contracts come out and say, okay, NSSDA, you've got to meet this standard. They calculate root mean square error, plug in with the confidence interval 1.96 at the 95% confidence interval, give this value of what NSSDA is, and these days we have no problem getting better results than the NSSDA. So even though there's some issues with the calculation, from a practical standpoint, there hasn't been issues with using that. We'll get at the end of this module, we'll talk about the ASPRS standard that's come out recently in 2014 that fixes that from a more digital data standpoint, okay? But this is the standard, so you have to kind of understand what's going on there, okay? So that was vertical accuracy, horizontal accuracy, basically the same kind of thing, except now instead of looking at one value, Z, you're looking at two values, X and Y, okay? So X and YR are the reference coordinates, X and YM are the map coordinates or the image coordinates, and it's basically the exact same process as you can see there. Now you're subtracting the reference coordinate from the map coordinate in the X direction and the map coordinate from the reference coordinate from the map coordinate in the y direction, okay? And then you're squaring those, adding them together, and then taking the square root of the sum of all of those, okay? So it's exactly the same process. The equation is a little bit more complicated, and it's complicated by the fact that now you've got a circular distribution. You don't have a single variable. We've got two variables. We've got an x variable and a y variable. Okay, and so you've got this circular distribution that you have to deal with. And big deal, it assumes that it's circular. It assumes that the errors in the x direction are equivalent to the errors in the y direction. And that is another assumption that may not hold. So again, there's a lot of considerations. There's a lot of things that you have to think about here. But you can see the equations are pretty straightforward, just like they were for the vertical, except they have the complexity now of incorporating both the x direction and the y direction, okay? And so again, probability distribution of the error around RMSE in a horizontal direction, same kind of thing. Z is now from the bivariate standard normal distribution, okay? So not a single variable anymore, so it's not just a straight Z, it's the bivariate standard normal. That changes things a little bit. Again, it's not a measure of confidence, it's just an interval, so just the same as vertical. And it is merely an estimate of the distribution of errors at specified levels of probability, again, assuming that the errors are normally distributed and assuming that the errors in X are equivalent to the errors in Y so that we get the circular distribution. Okay. Same problem with NSSDA. Again, it makes the same mistake. It substitutes root mean square error for the standard deviation. And so that error interval at the 95% is incorrectly estimated using this equation, 2.4477 times the root mean square error, where the 2.477 is probably not a number you know about, but it's the Z statistic at 95% confidence for a circular normal distribution for the bivariate normal, okay? And so then you calculate that, and you get the equation that the NSSDA for horizontal accuracy is 1.7308 times the root mean square error for horizontal, which is the standard equation. That's what the standard says, but it's got an issue with it, as I already mentioned. That issue is a minor issue because these days we're doing so much better than what NSSDA states we have to do. And so not a big problem, but you do need to understand that there's a problem with this, okay? So what's the summary of these issues, okay? One, NSSDA assumes the errors are normally distributed. That's not always the case. Second, it assumes that RMSE equals 0. That's definitely not the case. It mistakenly uses RMSE then as the standard deviation for the vertical or the horizontal to calculate the interval. That works if RMSE is equal to 0, but when it's not, it doesn't work, okay? So that's very, very important. So this is the equation that's used in the standards and the one that's relied on ubiquitously. It's the one that's used in the United States. So you do have to understand this. You will see lots of reports that show the NSSDA and that the value of NSSDA is such and such, and then the report shows that the map itself has errors less than NSSDA, and therefore it's okay. And that's why it's still important to understand this, even though there's some issues with this. Hopefully we're moving away from this. I'm hoping FGDC and others adopt other methodologies, but right now the standard of FGDC is NSSDA, okay? So you need to understand that. Here's the hope right now. The hope is this new standard set up for geospatial data. It's for digital data. Okay? And so it makes great strides in bringing this positional accuracy standard fully into the digital world. You know, historically, the standards, including NSSDA, were based more on hard copy maps because that's what existed back then, okay? It represents a really large improvement in the practice or application of positional accuracy. It still maintains the substituting of root mean square error for the standard deviation in the calculation of NSSDA. So it doesn't correct that issue. And so there's still more work that needs to get done. Okay. Luckily, there's software that calculates all this for you. So if you're going, oh, this is way too much for me to possibly deal with, that's not a big deal. You can calculate root mean square error. It's actually not difficult. In the introductory modules, I gave you an example. If you want to go back and look at that with a table, if you want to go into our book, there's samples and examples in there, and you could find this in lots of other textbooks related to positional accuracy. Okay, so it's there all over the place, and you could definitely look this up in more detail if you were interested. All right, so what did we learn from this lesson? Well, we explained some of the sampling that's needed to collect the reference data for positional accuracy. Want to make sure that you understand that the data has to be well distributed, and we use the ASPRS method for doing that. That incorporates spatial autocorrelation. So we separate the samples. We have to make sure the samples are independent. We have to make sure that they're easily identified. We have to these days consider that we might be taking data in heavily vegetated places. And so we might have different map classes that we use to help with that. Okay. We defined root mean square error. We showed the equations for that. Those equations are not difficult. Show the calculations. Again, go back if you want to and look at the introductory modules that I talk about, and it gives an example in there with the table. We discussed the issues involving NSSDA, the problem with using root mean square error instead of the standard deviation. We presented both vertical and horizontal methods. Okay. Vertical is easier because it's a one dimension. Horizontal gets a little bit more complicated because we're talking about 2 dimensions, X and Y. There's a lot of assumptions that go into that, assuming normality, assuming a circular distribution. And we talked about how the 2014 ASPRS standards are pushing us beyond NSSDA and much more into the digital world, which is a good thing. And I encourage you to look into that standard that's published out there and easily obtainable so that you can see what's going on there. Okay, so hope you enjoyed the 2 presentations on positional accuracy, and next time we will start jumping into thematic accuracy assessment in more detail.